Hey guys, welcome to Learn Today IGCSE. This is a tutorial video for space physics practice questions from Cambridge Assessment International Education. There are 8 MCQ questions from paper 1 and 5 theory questions for paper 2. Alright, let's get started. Question 1. Which row in the table correctly lists as a galaxy, a planet, and a star? A galaxy is a large collection of billions of stars, and the name of our galaxy is the Milky Way. Mars and Earth are all examples of planet, and our Sun is the only star in the solar system. So the answer here is B. Question 2. The orbit around the Sun of a comet is not circular. It's known as elliptical. The distance between the Sun and the comet varies as shown in the diagram. So P here is the furthest distance from the Sun, and R here has the closest distance from the Sun. The gravitational potential energy decreases as planet gets closer to the Sun, and as this potential energy decreases, its kinetic energy increases. So according to the conservation of momentum, kinetic energy is directly proportional to its velocity. So as your kinetic energy increases, so does the speed. So this will create a slingshot effect and push the planet further from the Sun. As it travels to the furthest distance from the Sun, the gravitational potential energy increases and its kinetic energy decreases. So as the kinetic energy decreases, so does the speed. Where in the orbit is the speed of the comet the greatest and where is the smallest? So the speed is greatest at R and the speed is smallest at P. So the answer here is D. Question 3. The orbit around the Sun of a particular asteroid dwarf planet is not circular. The distance between the Sun and the asteroid varies as shown in the diagram. The asteroid possesses both gravitational potential energy and kinetic energy. So this question has a similar principle as the one that we did before, which energy transfer takes place as the asteroid moves from X to Y and as it moves from Y to Z. So again, this is the position whereby the planet is closest to the Sun, so it has the highest kinetic energy and the lowest gravitational potential energy, whereas at X the position is the furthest from the Sun, so it has the lowest kinetic energy and the highest gravitational potential energy. So moving from X to Y, it will change from gravitational potential energy to kinetic energy. As it goes closer to the Sun, the speed increases. So the answer is either A or B. As it moves from Y to Z, so the same thing happens here. The gravitational potential energy will all convert to the kinetic energy. So the answer here is A. Question 4. Ceres and Vesta are 2 asteroids dwarf planets that orbit the Sun. The orbits of Ceres and Vesta are approximately circular. If they are approximately circular, this means the distance from the Sun at all time will be the same. Therefore, there will be no changes of kinetic energy or no changes of gravitational potential energy as they move. The Sun's gravitational field at the orbit of Ceres is weaker than that at the orbit of Vesta. So this tells us that Ceres is placed further from the Sun as it is from Vesta. Hence the reason why Ceres has a weaker gravitational pull due to its distance from the Sun, which is very far away. How does the orbital speed of Ceres and its orbital period compare with the orbital speed and orbital period of Vesta? Since Ceres is further away from the Sun, the speed would be smaller compared to Vesta, but it would have a larger orbit that orbits around the Sun. So the answer here is B. Question 5. The Sun emits energy in the form of electromagnetic radiation, which 3 components of the electromagnetic spectrum account for almost all of this energy. From your chapter 3, you will come across the electromagnetic spectrum. Make sure you remember the name of all the waves from the lowest frequency to its highest frequency. And make sure you know that the 3 components that account for almost all of the energy from the Sun is infrared, visible, and UV light. So the answer here is C. Question 6. When, in the life cycle of a star, are heavy elements produced? When there are no more elements for the star to fuse, the core shrinks to its gravity and collapses, creating a large violent explosion called supernova. During this explosion, it will produce heavier elements such as gold, silver, and uranium. So the answer here is when a red supergiant explodes. Question 7. The statements J, K, L, and M describe different stages in the life cycle of a small star. What is the order first to last in which the stages occur? Make sure you are familiar with the life cycle of a star for a small or a medium star, which is similar as our Sun, or a star bigger than ours, which is known as a red supergiant. The question here only wants us to know for the life cycle of a small star. So initially you have a cloud of dust and gas pulled together by its gravity to form a protostar. And when the forces are balanced, it's known as the main sequence, which is our star, and it is fueled by hydrogen gas, which will go through nuclear fusion to form helium. If the star is the same size as our Sun, it will turn into a planetary nebula, becoming a white dwarf, and cools down to turn into a black dwarf. So the order here starts with J when it collapses due to gravitational attraction to form a protostar, and when it is stable it undergoes nuclear fusion, and then a red giant is produced, and finally a white dwarf is produced. So the answer here is A. Question 8. What provides evidence for the Big Bang Theory? In your syllabus, you will learn two evidence. The first one is redshift, and the second one is cosmic microwave background radiation. So the answer here is B. The increase in the observed wavelength of radiation emitted by distant galaxy. This is what redshift means. Now let's move on to paper 2 example questions. Question 1. The solar system contains the Sun, planets, moons, asteroids, and comets. Question A. State the name of the planet closest to the Sun. Make sure you have memorized the order of the planet closest from the Sun until the furthest away. Question B. Describe the difference between a planet and a moon. So the difference is that a planet orbits the Sun, whereas a moon orbits the planet. State two differences between an asteroid and a comet. The asteroid belt are located between Mars and Jupiter, and asteroids are just large rocks that orbit around the Sun, whereas this is a comet, and comet is just a ball of ice and dust that orbits around the Sun. So one of the two differences between an asteroid and a comet is that comet comes from very far away, which is outside of the solar system, and it has highly elliptical orbit. And the second difference is that an asteroid is made of rocks, whereas a comet is a ball of ice and dust. Question D. The planet closest to the Sun orbits the Sun in 88 days. State two reasons why the Earth takes longer to orbit the Sun than this planet. One of the reasons is because the Earth is placed further from the Sun compared to the closest planet, meaning that it would have a larger orbit compared to this planet. So you can say that the circumference of the orbit of Earth around the Sun is larger. And another reason that it's taking longer is because our planet Earth is moving slower. Question E. State the time taken for light to travel from the Sun to the Earth. The time taken here is approximately 8 minutes or 500 seconds. Using your answer to E part 1, calculate the distance from the Sun to the Earth. Show your working. Okay, so we have here the time taken, which is 8 minutes. We know that the speed of light equals to 3 times 10 to the power of 8 meters per second, and we're looking to find the distance. Distance equals to speed times time, and since the unit here is meters per second, we have to use 500 seconds instead of 8 minutes. And we will get a value of 1.5 times 10 to the power of 11, and our unit here is meters. Question 2. Part A. A year, a month, and a day can be defined in terms of the motions of the Earth, the Moon, and the Sun. Using these motions, complete the following sentence. A year, or also known as 365 days, is the time for the Earth to orbit around the Sun. A month, or also known as 28 days, is the time for the Moon to orbit around the Sun. And a day, which consists of 24 hours, is the time for the Earth to rotate on its own axis. Question B. Earth, Jupiter, and Saturn are 3 planets in the solar system. Table 2.1 gives information about this planet. Using data from Table 2.1, calculate the average radius of Saturn's orbit around the Sun. So you are given here the speed and the time, and you're looking to find the radius, which can be calculated by the formula of orbital speed, which is 2 pi r over t. If we rearrange this formula, you would get something like this. So V here is the orbital speed, and the orbital speed for Saturn is 3.5 times 10 to the power of 4. Now the time taken here is 29 years. However, the orbital speed is per hour, so we have to convert 29 years to hours, which is equal to 254,040 hours. And we'll divide this with 2 pi, and you will get a radius of 1.4 times 10 to the power of 9 kilometers. Question C. Figure 2.1 shows one alignment with the Sun of Earth, Jupiter, and Saturn. Part 1. In Figure 2.1, the three planets and the Sun are in line. 29 years later, Saturn returns to the same position relative to the Sun, but Earth and Jupiter are not in the same line. Use the data from Table 2.1 to explain why. So from Table 2.1, we know that Earth takes 1 year to orbit, Saturn 29 and Jupiter 12. So in 29 years, Saturn has completed one complete rotation, and for the Earth in 29 years, it has completed 29 orbits around the Sun. And as for Saturn, in 29 years divided by 12, we know that it has completed 2.4 rotation around the Sun. So you can use this as the reason to explain why. Part 2. Complete Figure 2.2 to show the positions of the three planets exactly 6 years after the diagram in Figure 2.1. So we know that from Figure 2.1, these were the positions of the planet, and Earth takes 1 year to revolve around the Sun and return to its original position. So 6 years later, it means that the orbit would have completed 6 orbits around the Sun and returns to its original position. And for Jupiter, it takes 12 years for it to complete one full circle around the Sun and returns to its original place, meaning that 6 years after, it would have only completed half of the orbit around the Sun. So Jupiter would be here 6 years later. And for Saturn, we know that it takes 29 years for it to go around the Sun and come back to its original position. So now we need to find the position of Saturn after 6 years. So with a little bit of math, 6 over 29 multiplied by 360 degree, because a full circle is 360 degree, we would get an angle of approximately 75 degree, meaning that 6 years later, Saturn would have moved 75 degree, which is approximately somewhere around here. So this will be all the positions of the three planets exactly 6 years after. Question 3. Table 3.1 lists some of the planets in the solar system and their average distances from the Sun. From Table 3.1, we can see that the average distance from the Sun is increasing as it goes down. Part A. Complete the Table 3.1 by writing the names of the missing planets. If the distance from the Sun is increasing, this means that the order of the planet here should be from the closest to the Sun to the most distant from the Sun. After Mercury is Venus, and after Earth is Mars, followed by Jupiter. Question B. As the planets move around the Sun, the distance between Earth and Jupiter changes. Use Table 3.1 to calculate the smallest distance and the largest distance between Earth and Jupiter. The smallest distance between Earth and Jupiter can be obtained when they are both placed on the same side of the Sun. And the largest distance between Earth and Sun can be obtained when they are on the opposite sides of the Sun. So let's do the calculation together. The Earth is 1.5 times 10 to the power of 8 kilometers from the Sun, whereas Jupiter is 7.8 times 10 to the power of 8 kilometers away from the Sun. So the distance between them here is 6.3 times 10 to the power of 8 kilometers. So that would be the smallest distance between Earth and Jupiter. Now, as for the furthest, we can add up the distance of Earth from the Sun and the distance of Jupiter from the Sun, giving us 9.3 times 10 to the power of 8 kilometers. Part C. A planet is in orbit around a distant star. As it passes in front of the star, it blocks some of the light of the star from reaching the Earth, reducing the brightness of the star as seen from the Earth. Figure 3.1 shows the view from Earth as the planet passes in front of the star. So if the planet was here, so they're saying that as the planet goes in front of the star, it reduces the brightness of the star. We can imagine that if the planet was here, it will reduce just this part of the light from the star, and if it's in the middle, it will be reducing the most, and then as it goes away, it reduces again a part from the light from the star. Figure 3.2 shows an incomplete graph of how the brightness of the star varies with time, as seen from Earth. The planet is in front of the star from time t1 to t2, which is from here to here. So the brightness of the star as seen from the Earth is, let's say, at this level, but as the planet goes in front of the star, it's going to start reducing the brightness of the star partially until it reaches in the middle to block the most light of the star, and then as it goes away, it would increase back the brightness of the star. So from T1 to T2 until here, we can slowly show that the brightness decreases, and then it reaches a lowest point, which is in the middle here, and then it increases again, and as the planet completely moves away from the star, the brightness resumes to be normal. Part 2. Describe how the completed figure 3.2 should be changed to show a larger planet passing at the same distance in front of the same star. Okay, let's imagine. If this was a larger planet, it will block more light from the star, so the brightness that is seen from the Earth would appear to be lesser because more light is being blocked. And since it is bigger, it would actually take a longer time from T1 to T2 for it to pass from here to here. So for 2 marks, you can say it would appear to be lower brightness seen from Earth, and time T1 to T2 will take longer. Part 3 suggests how an astronomer uses the changes in the brightness of the star to measure the orbital period of the planet around the star. So to find the orbital period, we can measure the time when the brightness initially starts to reduce, which is T1, and then wait until the next time the brightness starts to reduce again. So this here would give us the orbital period of the planet. Question 4. When astronomers look at distant galaxies, they find that the frequency of the light from the galaxy is shifted towards the red end of the spectrum. So this question here is going to be discussing about the phenomena of redshift, which is one of the evidence that the universe is expanding. Question A, Part 1. Apart from visible light, state 2 types of electromagnetic wave that contain most of the energy emitted by a stable star. So we went through this from one of the MCQ questions. It will be infrared, visible, and UV. So you can write any of these two. Part 2. Describe what is meant by the red end of the spectrum. According to the dispersion of light, you will have different shades of color from red until violet. And the red end means that it has the longest wavelength or the lowest frequency. So you can write either one of this. Question B. The speed of recession of a galaxy is the speed at which the galaxy is moving away from the Earth. Astronomers use redshift to measure the speed of recession. Astronomers can also measure the distance of the galaxy from Earth. Such large distances are measured in light years. Astronomers can estimate the time t that the galaxy has been moving away from Earth using the equation. T equals to d over speed of recession. Table 4.1 shows their estimates for 4 different galaxies. So this is the speed in kilometers per second, and we can see that the speed increases when the distance of the galaxy from the Earth increases. However, the time here, which is approximately around 13.25 billions of years. Question part 1. State what is meant by a galaxy. A galaxy is a collection of billions of stars. Part 2. Show that 1 light year is equal to 9.5 times 10 to the power of 15. This question is exactly similar as the May-June 2023 paper 4.3 question 10. So we know that the speed of light in vacuum is 3 times 10 to the power of 8 meters per second. Since this measurement is calculated in seconds, let's convert 1 year into seconds. 1 year consists of 365 days, and each day has 24 hours, and each hour has 60 minutes, and each minute has 60 seconds. That gives us approximately 31 million seconds. Since 1 light year is a measurement of distance, let's find out if the distance would give us this value. So distance can be calculated by speed times time. So our speed here is 3 times 10 to the power of 8 meters per second. And the time here is 3.15 times 10 to the power of 6 seconds, giving us a distance of 9.5 times 10 to the power of 15 meters. So we have proved that 1 light year is indeed 9.5 times 10 to the power of 15 meters. Part 3. Describe the relationship between the speed of recession of a galaxy and its distance from the Earth. So as we have seen from the table, as the speed increases, the distance from the Earth also increases. Part 4. Explain how the value t provide evidence for the Big Bang theory of the origin of the universe. So looking at table 4.1, we will see that as distance increases, the speed of recession also increases, and we are always obtaining the same value of t. So as the galaxy moves further away from Earth, its speed increases, and if we calculate it, we always get the same value. Now if we backtrack this, if the galaxy was at a shorter distance, the speed was slower, and reducing the distance even more, the speed was even lower. And now if we go back to a value of t 13 billion years ago, we will get a distance and the speed all beginning at one point. So the value of t here tells us that all galaxies and Earth were together 13 to 14 billion years ago. The final question 5. A. The Sun produces energy from nuclei of hydrogen. Hydrogen nuclei are positively charged. This here is when hydrogen atoms fuses together to form helium. We call this as nuclear fission. Describe the process of that produces this energy. So we'll repeat what is being explained here. Part 2. Explain why this process needs a high temperature to occur. Both hydrogen atoms are positively charged, and lightly charged atoms would repel each other. So in order to fuse them together, that's the reason why you're going to need a very high temperature. So you can say that the nuclei will repel each other. So a very high speed and energy is needed for them to fuse together. Question B, Part 1. Some stars are initially more massive than the Sun. Describe the life cycle of such a star after it has passed through the stage of being a protostar. So we are asked to describe for a star which is really big, more massive than our Sun. After protostar, it would become a main sequence, which is a stable star, and then it expands to become a red supergiant. And then it turns to become a supernova and throws off its outer layer, and the core would become a neutron star, or if the mass was massive enough, its core would shrink to become a black hole. The life cycle of a star is a very common question, so make sure you know how to answer them. Part 2. Although the early universe contained only light elements such as hydrogen, it now contains a number of very heavy elements. State in which part of the life cycle of a star these very heavy elements are formed. We went through this in the MCQ question previously. This happens during the explosion of a supernova. That's all for this video. Thank you for watching. I will be uploading another set of space physics practice questions that discusses paper 1 until paper 4. Stay tuned. Thank you. Bye bye.